good afternoon and good morning or good evening. My name is Jinghui Yan. I'm a vice chair for the technical thrust for computational fluid dynamics and fluid and structure interaction of USACM for computational mechanics. Welcome to our virtual seminar series. Today's webinar will be given by our distinguished colleague Arif Masud. He will talk about variational multiscale discontinuous Galerkin method for coupled fluid-solid systems, theory and application. So before we let Arif do his presentation, I want to briefly introduce Professor Arif Masud. As a colleague of Arif Masud at the University of Illinois, I know how much accomplishments Arif has achieved. So I generate a slide to introduce Professor Arif Masud. So Professor Arif Masud is currently holds the John Allen Blumenschem Professorship in the Department of Civil and Environmental Engineering. He is also has a joint appointment in the Department of Aerospace Engineering. Although Arif didn't mention this in his bio, but I also know he also has an appointment in the Carl Illinois Medical School at the University of Illinois. So Professor Masud has made a fundamental and a pioneer contribution to the development of a variational multiscale method for fluid and solid mechanics, including variationally derived closure models for turbulence, stabilized method for Newtonian fluids. He has also developed the variational multiscale discontinuous Galerkin class of a coupled method for discrete interfacial mechanics in fluids and solids, and the stabilized method for mixture theory models involving coupled or chemo-thermal mechanical process in the modeling of materials. Professor Masud has received so many awards for research excellence. So here I select some of them. Professor Masud basically is the fellow of all the major society in engineering and in mechanics. So he's a fellow of USACM, a fellow of Engineering Mechanics Institute, a fellow of US Association for Computational Mechanics, a fellow of International Association for Computational Mechanics. He's also a fellow of Society of Engineering Sciences, a fellow of American Academy of Mechanics. He's also associate fellow for American Institute for Aeronautics and Astronautics. Recently, Arif Masud received the G.I. Taylor Medal in 2019 for fluid mechanics from the Society of Engineering Mechanics. And this year, Professor Masud received the Ted Binichio Applied Mechanics Award from Applied Mechanics Division of USACM. In addition to research and teaching, Professor Masud also distinguished himself in the professional service to our community. Here I just listed two of them. He is the president of elect of Society of Engineering Science. He's also an elected vice president of Engineering Mechanics Institute of USACM. Besides this leadership, Professor Masud also is on the editorial board of many top leading journals in computational mechanics and applied mechanics. So it is my great pleasure to introduce you, Professor Masud, and thank you very much for accepting our presentation. So now the floor is yours, and we are looking forward to to listen to you. Thanks.
Thank you, Junwei. Thank you very much for your very kind introduction. I also want to thank the organizing committee and the technical thrust area of USACM on fluid mechanics and fluid structure interaction for inviting me for this seminar today. What I'm going to discuss today is a variational multiscale discontinuous Galerkin method for multifield problems that are governed by multiple coupled PDEs. And I'm going to present ideas in the context of coupled fluid solid systems. And I'll discuss it with respect to two types of fluid solid interaction problems. One, which have a dominant interface between fluid and solid subdomain, and the other in which fluid solid systems are interacting on overlapping domains. So the ideas that I'm going to present here were developed in works together with some of my former students and current students that I will talk and I discuss their work here. So this slide presents the classes of fluid-solid coupled problems. The top row shows problems with distinct interface between fluid and solid subdomain, as shown here. Free flow, which gives rise to large interfacial deformations of this freely oscillating beam, or flows in blood-artery interaction, where the blood is modeled as non-Newtonian flow and artery wall is anisotropic. And here is a calcified artery, so artery wall also has different mechanical material properties that vary an order of magnitude. So these are very interesting fluid structure interaction problems. And then there are problems that have solids that are immersed in the fluid domain, where we do not have a precise nodal lines and mesh nodal points to define the surface of the geometry of the solid. And so the solid surfaces are immersed. And this is another very important class of fluid structure interaction problems. In engineering mechanics and engineering sciences, we have another type of problems in which fluids permeate through solids, chemically react with solids, trigger chemomechanical deformations, local deformations that give rise to steep fronts. And these processes take place in additive manufacturing, in even in the modeling of tissue material. In this class of problems, fluid-solid equations, they interact with each other on overlapping domains. And what I'll try to show is that the complexity of mathematical issues and the technical details of mathematical constructs that are needed to develop stable and convergent methods for this class of problems share same features as we see in the conventional fluid structure interaction problems. So the focus of my talk today is going to be on method development. So here is an outline of what I'm going to present. I'll first present the mathematical outline or structure of variational multiscale methods to show its enhanced stability and accuracy properties. And then we will embed in this framework ideas from discontinuous Galerkin method to give rise to the VMDG class of methods. We worked on these methods for some time. We first developed them in the context of frictional interface modeling in solids, extended to finite deformation of solids. And today, I'm going to talk about how we can extend these methods or apply these methods to coupled fluid structure systems. And an added feature of this method is it provides us the attribute of using matching or non-matching discretizations along finitely deforming interfaces. Then, as I mentioned, that there is other class of problems that have embedded interfaces in the background mesh. And I'll show that we can apply one-sided VMDG method, and it gives rise to immersed boundary methods. I will talk about chemically reacting flows infused through solids, giving rise to large local deformations and the technical issues associated with them. They give rise to advection-dominated cases, reaction-dominated cases, and we'll talk about stabilized methods developed within the context of variational multiscale framework to address these problems. Finally, I will round off my talk with some concluding remarks. So let's look at the underlying structure of variational multiscale method. Let's look at the model problem. Here, L is the differential operator, use the unknown function, F is the source term. For solid mechanics, this would be operator of elasticity, linear or nonlinear. And for fluid mechanics, these are the operators for Navier-Stokes equations. We define the appropriate spaces of functions for the problem that we have in hand, and we integrate it over the domain. That becomes the weak form. We make a mesh, we solve the problem. Now this signal here shows the overall signal, and with a decent mesh and a good method, we are able to capture the mean feature, and the small fluctuations about this mean are filtered out. And if you want to capture the small fluctuations, we normally need to refine the mesh. But if you see, this line of thought can be fairly restricting because we need finer and finer meshes if we want to capture finer physics. So the question to be asked at this point is that is it possible that we can develop a numerical method, a mathematical framework and numerical method that can capture the main features and can also account the effects of these fine scales while doing computations on cruder discretization. With that line of thought, if we look at this total solution, what we capture is the computed solution, and what is left is the error. Error is also a solution to the governing equation. So we write the total solution has a part that can be computed, a part that is beyond the computational capacity is the error. And in the context of nonlinear problems, this additive split should be looked at in the context of projections. Whether this operator is linear or nonlinear, its weighting is always linear. So we can split the weighting function likewise into coarse and fine and plug it back in here, and it gives us a multi-scale weak form. And this also becomes a departure from the standard Galerkin methods. Now, the general framework is as follows. We can split this problem into a coarse scale problem, which is weighted by the coarse scale weighting function, and a fine scale problem that is weighted by the fine scale weighting function. And today's talk is going to focus on this fine scale problem, how to extract expressions for fine scale models that can be embedded in the coarse scale framework. And there was a paper in 2008 where we used a generalization of residual free bubble method applied directly at the fine scale level, and it provides us an avenue to extract analytical expressions for fine scales under suitable assumptions. So we can see that the fine scale can be written as a residual of the coarse scale. Suppose we are doing a nonlinear problem, nonlinear solution. So U bar is the computed solution. So what you got from the previous step or previous iteration, if you take it to the right-hand side, we see that the fine scale, in fact, is driven by the residual of the Euler-Lagrange equations. So it is a residual-driven method. So it is variationally consistent. So we can write down X fine scale as a function of residual. And through this framework that I'm going to present, we will get an analytical expression for the stabilization tensor. R is the residual. We can plug it back into our fine scale, into our coarse scale equation here, and we get this modified form. The black terms are the Galerkin terms, which are present there. So Galerkin method is fully preserved. In addition, we get these two terms. They are now modeling the effect of fine scales U prime. So fine scales have disappeared, but their effects are being modeled. And once we get this solution, we can go back to this problem and we can substitute the computer solution here, and we have a posteriori error estimator built into this framework. And we will take advantage of both of these ideas. So now let's look at idea of putting together, coupling dissimilar PDEs across interfaces. But before we do that, let's look at how to develop a domain decomposition method for an equation that governs over the entire domain. We cut the domain at this interface. So the governing equation is now active or governs the phenomena inside of both the domains. But at this interface, we now need to enforce the continuity of the field and its flux. There are different techniques that can be applied here: Lagrange multiplier, penalty function, motor methods. That can be a Nietzsche method that can be applied in here. We'll start off with Lagrange multiplier method to enforce this continuity, and then I will show through the constructs that I'm going to show will follow how we can get an expression for the Lagrange multiplier. So the idea is as follows: that at this point we are enforcing the continuity. So as compared to the continuity that was there in the beginning in this problem, this weak continuity is going to introduce some errors. So question is, can we use the notion of error in the VMS framework applied locally at this point, and can we derive those error terms? And maybe those terms can provide us a way to couple these two techniques. That is the underlying idea, and that is what we will capitalize on. So we have this, the field is the domain boundary operator that is related with domain interior operator, and it acts on the field in the boundary. Lambda is the Lagrange multiplier. B is the trace operator that takes the field, projects it on the boundary to couple it with the Lagrange multiplier. So here is the interfacial weak form where we have through Lagrange multiplier enforce the balance of flux and continuity of the field. Now this problem, in the continuum sense, it inherits there is inherent stability, but its discrete version does not inherit that stability. There are a couple of issues here that arise. Since this gives rise to a mixed field problem, not all combinations of interpolation functions for Lagrange multiplier and underlying field are stable and convergent. So we need some kind of stabilization in there. And secondly, and most importantly, from the material modeling perspective, Lagrange multiplier has a connotation of force type field. It can tell you how much force is needed to keep the two pieces together. But if you have interfacial kinematics, and that typically happens in solid mechanics problems, then Lagrange multiplier cannot model it. Penalty function cannot model it. So we will develop those equations. We'll develop a system of equations to be able to account for that. So we assume an additive decomposition of the solution add this interface into a coarse part and a fine part. Fine part is now in the context of errors. We will develop a VMS framework locally around this interface and locally resolve this fine scale problem here. And I'm showing you the general structure, and I'll show it for fluid structure interaction and a couple of the problems that this is the structure that will come out. The terms in the black are the domain interior terms, Galerkin terms, and the terms in the blue are the terms that will appear. And these terms, the first three terms, are similar to the DG method or interior penalty method. In addition, we will be getting analytical expressions for the stabilization parameters here, or stabilization tensors here. This is a least square form of the flux continuity term, and we have applied it for solid mechanics. We have applied it to finite deformation, thermomechanical problem, and today I'm going to discuss them in the context of fluid structure interaction, especially undergoing large deformations when you have anisotropic solids on one side. So let's look at the governing equations for fluid structure system. We write the fluid equations in the current frame in an Ale frame, arbitrary Lagrangian area, to be able to account for large deformation of the interfaces. The continuity equation and the boundary and the equation for being able to move the mesh. So this is mesh motion. For solid problem, solid mechanics, finite deformation is given in the reference configuration, and we'll need to push it forward to the current configuration to couple it with the fluid. And I will highlight that this becomes very important for materials, especially if they have directionality in them. So interface conditions means V1 is the velocity of the fluid, which will be coupled with the velocity of the solid at that point, which is projected back from its reference configuration. This is the stress at the interface from the fluid, and stress from the solid is coming through this hyperelastic relation. Now, we have a weak form from the fluid in the current configuration and a weak form from the solid, which is first developed in the reference configuration and then pushed forward to the current configuration. And that is where we are going to couple these two equations. For notational simplification, let me call it the B Galerkin, F Galerkin, and B solid Galerkin and F solid Galerkin. So we are going to couple these terms together with Lagrange multiplier, and this is the Lagrange multiplier formulation written in the current configuration in this domain here, this shaded domain here. So the balance of tractions and continuity of the velocity field. Now, as I mentioned, that we are going to use the notion of additive split of the velocity field into coarse and fine. And fine, you can think of it, as I mentioned, we can think of it as the error, something that we are not able to compute at this point. And likewise, the weighting function is decomposed into coarse and fine. So fine scale will have the notion of scales, not computable scales beyond the resolution capacity inside the domain, and they will have the connotation of error at the interface. So fine scale give rise to two problems: a fine scale problem in the domain interior, omega minus this band over here, which is right next to the interface, and a fine scale problem that is defined at that interface. We will exploit this structure in my talk today to derive an interface coupling method. So we'll focus on this particular point, and VMS-based stabilized methods can then be injected in the final stabilized form. So the derivation of interfacial coupling terms is a three-step process. Step one is linearize the fine scale problems from the fluid and the solid at this interface and localize this to a narrow band here. And now what we are going to do is we are going to express them in terms of edge functions. These are functions which are non-zero along this edge, this segment, and they become zero on the other edges. So it means that the first layer of elements on both sides are going to take part in this coupling process and in giving rise to those coupling terms. So the sport of bubbles is the red dashed area. And since we are not enforcing the continuity of the field, so we have the luxury to have non-matching meshes at interfaces. And all what you need to do is make sure that we create these segments by projecting the nodes on both sides. And then we do this integration segment-wise. We solve it segment-wise. And that's the only thing that is needed to couple the two together. So we solve for the fine scales independently, sector-wise, from the fluid and from the solid. And we will get the fine scale expression for velocity from the solid and from the fluid, but in terms of the Lagrange multiplier, which is an unknown. So the question then is it possible that we can also get an expression for the Lagrange multiplier, for which we need another equation? And for that, we will go to the coarse scale continuity equation. And I will now show you how it is done. So we look at the fine scale problem. We linearize in the current configuration. This is the linearized fine scale problem. We write the fine scale problem for solid. Linearize in the reference configuration, push it forward to the current configuration. So these are the two equations that we are now going to solve segment-wise. And we, as I just showed, we are going to use these functions, bubble functions or edge functions, to expand the fine scale fields in both of these. Now, the fine scale problems can be further simplified to make the terms tractable. So one option that we use is we say that these functions, the edge functions, are talking to the domain interior residual, and we can drop these. And this substantially simplifies the derivation of the method. And now we can further make it, and as we can further use mean value theorem on these coupling terms, these magenta terms, and that will pull this residual out. And now it's very easy to solve it for lambda on either side at this interface. And when you do that, you get an expression that looks like this. So fine scale velocity from either side, alpha equal to 1 is fluid, alpha equal to 2 is solid, is a function of the residual of the flux at the interface. And T is the flux, and here is T for the fluid domain and T for the solid domain. So we see that the constitutive model is fully represented even at the edges. So material constitutive model are fully accounted for. In addition to this, an important thing that we see here is that the structure of the stabilization tensor appears naturally. And this stabilization tensor is a composite stabilization tensor, because on one side is fluid, and the tau for fluid has this particular form. And you can see that the equations or the operators of Navier-Stokes equations are working on the fine scale functions, edge functions, to give us this expression. And while for the solid, it is the operators of nonlinear elasticity that are acting on this field. So these are unambiguously, we can completely derive them. And tau is a composite function, and T, so it means that the error at the interface is going to be, we can account for all the features there, both the equations, the material properties, and also the change in geometry, as I will show for final informations. So as I mentioned, the fine scales still had Lagrange multiplier. For that, we can go to the coarse scale continuity equation. Coarse scale continuity equation had jump in velocity. Velocity has coarse part and fine part. We can open the fine terms and substitute velocity from either side. Now, at this point, our objective is to be able to extract an expression for lambda. Now, since we are developing stabilized methods, one attribute of stabilized methods is that we can use arbitrary combinations of interpolation functions for Lagrange multiplier and for the unknown field. One option that we can use is piecewise discontinuous Lagrange multiplier, and we can take it out of the integral expression, and locally resolving it, we get expression here, where T is the average weighted traction vector, which is weighted by these parameters delta that are function of tau. So everything here is analytically derived. V bar is the jump in the coarse scale velocity field, and tau is expression that I showed you on the previous slide. We can now substitute lambdas and fine scale velocities in the coarse scale form, and this is the VMDG form for FSI, where we have domain interior terms for fluids and for solids, and we have these terms have emerged because of the procedure that I showed to you. The first two terms are consistency terms. This is the balance of tractions. This is the continuity of the velocity. This is a penalty term, and here is the least squares form of the stress term at that interface. Now, to this formulation, we can always add the stabilization, domain interior stabilization. And if you wanted to derive this domain interior stabilization using VMS ideas, you can go back and so apply that idea in the domain, and these are the terms that will come out. So now let me show you an example problem. Here's flow-induced vibration. Flow comes on, gives rise to vortices. There's a flexible beam, undergoes large deformation. We are going to look at two different real number 100 and 1500 for meshes that are matched and meshes that are non-matching meshes. An objective is to develop non-matching meshes. Here is the Reynolds number equal to 100, and we are getting very close solution between matching and non-matching meshes. This is to validate that this techniques that we have developed, they are variationally consistent. They're not introducing anything artificially into the system. Here is the response for Reynolds number 1500 and snapshot of vorticity for 100 and for 1500 for velocity and pressure. Here's the zoom view for matching mesh and non-matching mesh for vorticity, and we get similar qualitative response. Here is the pressure, and again, qualitative response looks similar. This is the displacement profile of the beam when it is moving from lower end to the top, from bottom to the top, at different points for matching and non-matching, and we get very closely matched response for both the cases. Now, as I said, that we have stabilization tensor, we can have analytical expressions, we can look at the magnitude of stabilization tensor, and this is an important thing for large deformation problems. There is enough literature out there that says that stabilization tensors should be a function of large deformation of solid, and therefore some guiding principles have been laid out, some outlines have been laid out. But if you go through this route, you can exactly find the expressions, and we have plotted it for 3 different time points, and you can see that Lagrange, this interfacial stabilization tensor, for a given point in time varies spatially depending on the local features in the flow here, and at a point it varies as a function of time as you go through the process. So it varies both as a function of space and time, and it has features of area averaging and stress averaging built into it. You can also show that these stabilization tensors are positive definite. For solids, this is very straightforward. For fluids, we have shown a proof here in this, that under reasonable assumptions, this and for advection dominated case, if we take the skew part and use advection bubble there, we can show that the stabilization tensor is positive definite. Numerically, we can validate it by looking at the eigenvalues. For example, for this snapshot, we looked over all the elements and we looked at on this edge, and we found the maximum and minimum eigenvalues in this frame. So minimum eigenvalues over all the elements along this edge, all the segments on the edge was in this range, and maximum was here, and likewise for all the points. So it's bounded all the way through. Now let's look at some applications, interesting applications for large deformations. This is thoracic aorta, this is geometry, material is Newhookian material, and blood is incompressible Newtonian, matching and non-matching meshes. And important things I want to show here is that invariably for fluid mechanics, we have high resolution close to the boundary because we want to capture the boundary layer region. But if we are restricted with matching meshes, we are overly restricting the solid mechanics problems. And if we have non-matching mesh, we can considerably reduce the number of unknowns. So we can reduce the size of the problem by 23% of nodes or 31% elements. And it also provides us flexibility that we can model the fluid part and solid part fairly independently and then couple them together. I'll show you some numerical results here. Now this is the vorticity inflow, and we'll be looking at outflow rates and pressure drop along this length. Here's the wall shear stress at systole, and we are looking between matching and non-matching, fairly comparable results, and wall shear stress at diastole, and again, fairly comparable results between the two, matching and non-matching discretizations. Here's the flow rate at the inlet and outflow rate with matching and non-matching meshes, and again, close correlation. So it means that the method that we are providing for coupling together non-matching and matching meshes is accounting for all of these features. And here's the pressure drop along the main branch. So now that we have this framework, let's apply it to a more interesting problem. Here is a patient-specific calcified artery. So this calcification is an order of magnitude stiffer than the artery, and artery wall by itself is modeled with the Newhookian material with an embedded anisotropy, where M is a second order tensor that accounts for this anisotropy. The blood is modeled as a shear rate dependent model, and this artery wall system is embedded in a tissue material. So external tissue support is modeled with Kelvin type model. So here we are looking at wall deformation, fluid velocity inside this constrictions, and wall shear stress and fluid vorticity. And again, flow rate versus time and pressure versus time between matching and non-matching discretizations is virtually similar. This slide shows some snapshots between matching and non-matching meshes, wall deformation and streamlines at peak systole, mid diastole, and here we are looking at wall shear stress at the interface and fluid vorticity inside the fluid domain for matching and non-matching meshes, peak systole and mid diastole. So with this in hand, now let's look at how about can we use this idea to develop immersed fluid-solid methods, where fluid-solid interface is an immersed interface which is not precisely represented by the mesh node lines. And in order to develop that, we will be applying one-sided VMDG method. So here is this a diagram. Inside is the fictitious domain, outside is the fluid, and this is the boundary. And you can see it is not coincident with any of the boundaries of the mesh node lines. So we have this fictitious elements, which we can completely take out. But then we have elements which are traversed by the interface. A part of it has fluid, the other part is a part of fictitious domain. So we will be now applying it to this magenta color. We will be applying the VMS idea one-sided in this framework. So we can apply Lagrange multi-formulation. This is what you saw. This is a Galerkin form of the Navier-Stokes equations in the domain omega f. And we have the Lagrange multiplier enforcement of natural and essential boundary conditions. We do a scale decomposition along this interface into coarse and fine scales, weighting functions likewise into coarse and fine scales. So it gives rise to a coarse scale problem, and it gives rise to fine scale problem in the domain interior. All the elements which are not shaded and are part of the fluid domain, they give rise to one fine scale problem, and we can use VMS-based, residual-based turbulence models to stabilize them. And we also have a fine scale problem in these elements, which I have color coded, and these need special treatment. And we will now focus on the next slides on these elements here. All right, so as I mentioned, the fine scale problem at interface in the elements that are traversed by interface is given here. We are going to follow similar lines. What we did in the previous case, fine scales in this time, we are going to retain them as time dependent because we want to have the fine scale fluctuations of the velocity field as well. So we are going to enhance the model, fine scale fluid model that we are going to use here. We perform temporal discretization of the fine scale equation, linearize with respect to fine scales, localize it at the interface, and expand the fine scales via functions. And these functions now have this embedded interface or discontinuity embedded in it. So we use these functions which have this embedded in discontinuity for the interfaces inside the domain element. And to make the problem tractable, when we linearize it, we get the residual, interior residual. We invoke orthogonality of edge function with respect to interior residual. That makes the problem simpler, and solve the problem segment-wise, as I showed on the previous slide for FSI. So when you solve this fluid problem, one-sided VMDG, you get an expression for Lagrange multiplier and an expression for fine scale velocity. It's interesting to look at the Lagrange multiplier. It has the traction of the natural stress boundary condition on the surface and an adjustment with respect to any error in the velocity condition at the interface. And you can also extract or derive an expression of tau I. And when this is substituted in the interfacial velocity field, a very simple, it's very crucially important, very simple expression for fine scale velocity appears. And this can also be then used as a measure of error. So when we plug it back, we have the Galerkin form of Navier-Stokes equations. These are the additional terms that we have derived through one-sided VMS. These are the natural boundary conditions. This is the weakly enforced essential boundary conditions. And we can add to it domain interior stabilization, where in our work, we have used the turbulence model that was developed based on VMS ideas, where the first term takes care of the high advection effects for mass conservation, and these are fine fluctuations of the velocity field. We can also add ghost penalty type methods, which are a term. These terms are added along the embedded interfaces to control the oscillation of the velocity field. And in a paper in CMME in 2021, we showed that this ghost penalty term can be derived and can be shown to be a type of interfacial stabilization. So with these terms in hand, we can also get the stabilization tensor. And you can see that stabilization tensor has the effects of the domain interior terms in there, the operators in there. It also has the information about the cut facet, and this is represented in here. So it is fully accounted for the geometrical aspects of the cut elements as well. So let's now quickly look at how do we represent the interfaces or merged surfaces. There are different ways to do that. One is level set based approach. The other is surface mesh approach. Level set approach gives us a precise definition, but it's difficult to generate level set for complex geometries. Whereas we can use surface discretization based on CAD models. We have STL files. We can do surface triangulation and immerse them in the fluid domain. In both the cases, we need tessellation. We divide it into subsegments, define, populate them with the integration points. We're going to do domain interior integration, and we also do boundary integration. And these points that belong to the fictitious domain will not play any role in this process. If we are going to use surface mesh approach, then we need some kind of ray tracing method to figure out what integration points are within the computational domain of the fluid and what are in the domain which is the fictitious domain. So these are this is a standard technique that is used here. So let me show you a benchmark flow problem. So here we have a sphere which is fully embedded in the fluid domain. We have used 8-node hexahedra elements. This is a velocity streamlines and vortices. We have plotted the mean velocity in the wake of the flow. So, these are the results from our method, and these are the published results. A very good correlation on the mean velocity in the wake and the pressure on the surface. This is the schematic diagram of the pressure profile on the surface, and this is the computer pressure projected onto the surface. Since we have developed stabilization tensor as a function of the geometry of the cut element, so we have just taken out representative elements where we see the cut surface goes through the element or through a small portion of the element, and we see that for sliver elements, the magnitude of stabilization tensor increases, so it's inversely proportional to a length scale in there. But and it increases in magnitude as the size of the element decreases. As I mentioned, that we can embed in it VMS-based closure models for turbulence, and we developed this method doing a VMS split of velocity and pressure field into coarse and fine, and a further split. So fine scale problem becomes again a mixed field problem. It needs stabilization, so we do a second split of velocity field into a level 1 velocity fields, fine scale fields, and a level 2. So this is the successive split VMS-based split of the unknown fields, and this is the variational projection or building of the model. Projecting the fine scales at level 2 in level 1, stabilize this and make it an unconstrained level 1 fine scale problem, which can be resolved to extract expressions for V1 prime and P1 prime, and they become our closure models for turbulence. Using this idea, we developed this turbulence model, which we are now going to inject in the general framework. This is now flow around the sphere. Geometry is same. Reynolds number is 10,000. We are now using tetrahedral elements. Last one I showed you for hexahedral elements. Here we are using tetrahedral elements. No, the surface cuts through the domain. Here's the mean streamwise velocity and present results for 2 different time steps, and we are comparing with DNS results and NES results. Also plotted is mean velocity fluctuations and comparison of our results with the published results. Here is the pressure coefficient on the surface of the sphere and comparison with the DNS and NES. We have plotted mean streamwide velocity at a distance x equal to 1.6 in the transverse direction and mean velocity fluctuations, turbulent kinetic energy, and this is a measure of the energy in the system, of fluctuations in the system, and spectrum account for the fluctuations in the system. And we are, in order to quantify it as a turbulent flow, we need to look at how does it decay energy from larger scales to smaller scales. We've plotted the energy spectrum, and it shows this minus 5/3 column graph rate of decay of the energy. We can also look at the magnitude of interfacial stabilization tensors for the sphere case. Tau is proportional, inversely proportional to the area, and again for sliver elements, its magnitude increases. But as I mentioned to you, that the value stays bounded. These are the values of tau for smaller elements as a measure of some length scale of the element, sliver element. The magnitude increases for smaller elements, but when we look at the histogram, most of the elements stay in this range of 0.1 to 100, and the maximum value is bounded, it stays at 100. We can also look at the fine scales as a measure of how accurately we have applied the boundary conditions on the surface, because we have imposed it weakly, so we can we need to look at how accurate our results are. So we're looking at two views of the sphere. One is the front of the sphere, and now this is looking at from the side. And we see that the front of the sphere, because of the velocity coming on and because of stagnation point, so there is a slight increase in error, but the error stays bounded within 3% of the inflow velocity. And the blue error is very, very small compared to the other parts of the domain. So we can also quantify the quality of our solution for this particular case. Now let's apply this method to a more interesting problem where the geometry is more intricate. Here we have used the embedded method with surface triangulation. In flow conditions, mesh is composed of nearly 1 million nodes, 5.7 million tetrahedra, and surface triangulation of the geometry is done with 186,000 triangles. This is the snapshot of velocity and vorticity fields. We have plotted the, in order to look at the flow characteristics, we have plotted the energy spectra along this line. This geometry doesn't have a symmetry plane. So we have plotted along this line in the wake of the flow and in the vertical direction. And in both the cases, we see that the decay of energy from larger scales to smaller scales is generally following this -5/3 rule. Here is the vertical structure on the surface. In the beginning, the flow is attached, it detaches and goes into full-blown turbulent features. Here are the streamlines. For this problem, we can also look at the magnitude of stabilization tensor and stabilization tensor for all these different geometries. There is stagnation point on the side. We have separation of the attached boundary layer, but the magnitude stays bounded and maximum value is 500. And the errors in the boundary can also be looked at in the front at the nose cone where there is high velocity, and the side where the separation takes place. And the error is within 1% of inflow velocity, error in imposing the boundary conditions. So now, let's now look at, so we have developed some techniques for looking at fluid-solid interaction around discrete interfaces, whether they are represented by mesh nodal lines or they're embedded in the fluid domain. I want to point out that there's another class of fluid-solid problems that actually require same mathematical constructs that I was talking about. And this is the class of problems where a fluid permeates through a solid. So solid is a connected domain. Fluid permeates through it, chemically reacts through it. That gives rise to local advection reaction type effects, can lead to local change in phase in the solid and local deformations in solid. For that, we are going to use mixture theory model. So here's the micrograph where you can see the solid particles and is filled with fluid. So what mixture theory does is it doesn't model each and every solid particle or the fluid subdomain. It looks at it from a mixture point of view, and we segregate the fluid and solid proportional to their volume fraction, homogenize them, and then bring them together. So this is a homogenization, but this is local homogenization. If I take a small portion from somewhere else, its relative volume fraction for fluid and solid is going to be different. So it is locally homogenized, but globally it does retain that feature of inhomogeneity. Now, in addition to that, we want to develop a framework where we are not restricting the fluid to move with the solid. So we want to have an unconstrained framework where the fluid can flow past through this network or through this through the solid, porous solid. In mixture models, since we are not modeling each of the constituents, we account for the constituents via balance laws applied independently to each of the constituents. So we'll have solid balance of mass equation and solid balance of linear momentum equation. Likewise, for fluid balance of mass equation and fluid balance of linear momentum equation. Now, the question is, how do these two constituents know of the presence of each other? Now, in this system, as I mentioned, there will be chemical reactions taking place, as shown here. Solid interacting with fluid, which will give rise to a transformed solid or evolved solid, and maybe there is a byproduct of fluid as well. So chemical reactions are also taking place. These chemical reactions are going to give rise to change in phase from fluid to solid. In this work, we have looked at the change of fluid into a solid, so densification of solid. That is the reactions that we are considering in this work that I'm presenting here. So it means there is a mass transfer. So the fluid balance of mass, solid balance of mass, and fluid balance of mass have these reaction terms that account for change of phase from fluid to solid. And so loss of the fluid is the gain in the solid. Likewise, for the momentum balance equations, we have interactive force fields, and these interactive force fields account for the relative forces as the two continua move past each other. I'll show the structure of these interactive forces. So the two constituents not explicitly represented through numerical techniques, but rather represented through mathematical coupling of the two domains. Now, we also need to add constitutive models. In order to have apply constitutive models, we look at Helmholtz free energy for the fluid and solid. And once we have these functions, we can derive the expressions for the stress tensor for the solid when we plug it in this generic form. This is the mechanics part of the stress tensor coming from the mechanical deformation, and part of the stress tensor that is coming from solid chemical potential. And likewise for the fluid chemical potential and viscous drag effects that are adding to or contributing to the stress in the fluid. So in addition, as I mentioned, that there are interactive force fields. These interactive force fields have different effects, the gradient of density and temperature effects. In this work, the most important effects that we have accounted for are the mass transfer drag force and the viscous drag force. So I'm going to be focusing on these two terms. So when we make the Helmholtz energy functions precise, and here we have taken the Helmholtz functional for the fluid as ideal fluid, and for the solid, it's a functional that is comprised of elastic solid and a Lagrange multiplier enforcement of coupling between mechanical and chemical parts. Mechanical part is represented by B, which is the Cauchy-Green deformation tensor, and gamma is the reaction rate. So through this, we bring in the gamma mechanical coupling. When we plug these functions in these generic expressions, this is the expressions that we get for interactive force field and for the stress tensors for the fluid and for the solid. And you can see that the finite deformation effects are fully accounted for in the stress evolution for the case of solids. So now let's look at the standard weak form for the balance equations, the governing laws. We can write the standard governing equations by first defining the appropriate spaces of functions, which in most of the cases are H1 functions. So we have fluid balance of mass, fluid balance of momentum, solid balance of mass. And important thing to realize here is that in fluid balance of mass equation can become advection dominated for high advection fronts, or if there is a rapid chemical reaction taking place, it becomes a reaction dominated problem, which also is similarly perturbed. It gives rise to very thin layers or boundary layer effects. So advection dominated or reaction dominated, both need stabilization. Fluid balance of mass, for the case of low diffusivity, will become advection dominated or reaction dominated. So we need stabilization techniques here. And we are going to use VMS-based stabilization in this case. Now, if you look at solid balance of momentum equation, which is otherwise a very benign equation, diffusion dominated, but when we have interactive force field, an interactive force field brings in the chemical reaction terms in there for high chemical, high reactions or high rate of change between the fluid and the solid. This can dominate the process. And this solid balance of momentum equation can also become a reaction dominated, zeroth order term dominated equation, similarly perturbed equation. So the net thing is we need stabilization for this coupled system of equations. So I'm going to just outline the last few minutes, the VMS-based stabilization that we have used. You can follow the domain interior stabilization for the mass. These are the standard Galerkin terms. These are the stabilization terms, which you can derive. Here, xi is the adjoint operator. Tau is the stabilization parameter. It is fully derived. And you can see that the operators of the governing system are acting on the fine scale fields that are used to expand the fine scales in there. Likewise, we can do the same thing for balance of linear momentum for the fluid. These parts I had shown you in the previous slide. This is the additional term that will come in because it has now the interactive force field in here. And we have used a reduced form of the stabilization term because these terms will have can have interactive force field has a lot of terms. So you can look at it and see an order of magnitude analysis and see what are the dominant terms and only implement those terms in there. So here is the joint operator for balance of the momentum for the fluid and the stabilization tensor which is now fully derived. And these are presented in our paper in 2020. Let me show a couple of example problems. This is chemomechanical coupling, reacting fluid permeating through solid. This is a chemical reaction. Byproduct is silicon dioxide, which is 2.2 times the volume. And so we see oxygen going in. This interface moves across this interface. The chemical reaction is taking place. This is completely depleted solid. So phase change has completely taken place. And now the chemical reaction is taking place in the undeformed region. As the oxygen moves further, this length becomes larger. It becomes less difficult for oxygen to permeate through, and the rate of reaction drops. And this is what we capture through our numerical simulation. The solid line is the numerically computed results, and the dots are the experimental results. Here is another example where we have exposed the top surface to oxygen, silicon exposed to oxygen. The top surface expands and undergoes compression because the bottom surface is still original material. The material advects. So this is a reaction state. Blue means the material is completely depleted or reacted. Red means it is not reacted as yet. And so you can see the interface moving inside the bulk domain. Here is the distribution of stress and at the deflected shape. If you want to bring thermocamomechanical in this framework, you need to bring in an energy equation. Theta is the temperature field, and that will bring in the thermomechanical coupling. Phi is the phase transformation, and that will account for the portion of the domain where this chemical reactions have taken place. So the Helmholtz free energy will have temperature effect, and therefore the constitutive models will have temperature effect. And with this, the significant coupling effects that one can model is chemomechanical, where reaction-induced deformations, or thermomechanical, temperature changes induced thermal expansion, or thermochemical, where temperature influences the local reaction rate. So this becomes a very interesting set of problems. Let me show you this case where, again, it's exposed, oxygen comes in, reacts, this interface moves. This is the reacted state, completely transformed, untransformed. This moves through it. Here we are comparing it with experiments, oxidation thickness as a function of time, and oxygen growth rate as a function of growth and thickness. And we see that the growth rate drops as the thickness increases because it becomes harder for the reacting agent to go through the bulk material. Here is this case of thermocamomechanical process, material completely untransformed, and chemical reaction takes place, high temperature, and at this stage, it is completely transformed. So untransformed material is here. We are looking at compressive stresses. This is one of the interior points where reaction has gone up to this particular point. So temperature is, the stress is high in this region, and this portion is not reacted yet. Here, the chemical reaction is taking place all through the domain. Material is completely transformed, but it has not got enough time to dissipate the heat that is generated, and sufficient time passes. It goes to this thermal contraction, and it goes to uniform temperature over the body. Here are the fields as a function of coordinate reaction taking place. So where the reaction has taken place, reaction state has completely exhausted the material, is fully saturated with the fluid, and the other portion has not gone through the reaction state, and the fluid has not reached there yet. So, and this is the last problem I want to show. This is oxidation, and this problem is used in electronic industry to manufacture transistors. There's the surface is exposed to oxygen, undergoes light deformation. So you see this transformation along this interface. The interface moves. And it's a very crude mesh for this type of problems. Undergoes large deformation. Here is warm Mises stress, and we can also quantify the accuracy of the method by looking at the fine scales. So as my concluding remarks, I would say I would try to present a VMDG method for interface coupling in light deformation FSI problems. I wanted to highlight that for light deformation problems, you need to carefully look at the interfacing terms from solid and couple them appropriately at that interface. This method is consistent, and fine scale problems are residual different. So this is a consistent method. It inherits the notion of edge-based stabilization. This method can also be used for multi-grid patching for different PDEs. You can use this framework to couple different partial differential equations across the interfaces. The stabilization tensor, I tried to show that they possess many distinguishing characteristics: element size, aspect ratio, shape, polynomial order, material properties. These are inherently built into by derivation, not by design, by derivation. And that is an important message I want to give here. One-sided VMDG gives rise to variationally derived immersed boundary method. And again, all the parameters are variationally derived. And you can also look at the error in terms of imposing the essential natural boundary conditions on the boundary when you go through this route. I also presented VMS-based stabilization for mixture models for coupled chemomechanical problems. So our papers are on this website, and you can also find some simplified codes at this website. Most importantly, I want to acknowledge my students who have been instrumental in these works. Some of my former students, Tim Truster, who developed VMDG method together with me, Pinley Chen, who extended to finite deformation solid mechanics, Soon Bin Kang, who just finished his thesis and extended it to fluid structure interaction and immersed methods, Marcelino, who applied it to mixture theory models, and my current students who are working on these topics, and Li Xingzhu, who developed closure models for turbulence. Acknowledge the fundamental support from NSF, Air Force, and NIH, and the computing resources for these works. And these are the related publications. They're all on my website, and you're most welcome to see them. And if you have any questions, you can send me questions. I'll be most happy to answer your questions. So with that, I thank you all.
Okay, great. Thank you very much, Arif, for a very nice presentation. Now we open the floor for questions. So, Mike Rand, could you unmute yourself and directly ask your question? I saw you raise your hand.
Thank you, Professor Yang. Great talk, Professor Masud. I have a couple of questions. One question was, I noticed that the fluctuating velocity in the flow process sphere case was slightly over-predicted compared to the DNS. Do you have any comment on the source of this over-prediction? And part two would be, how are you implementing, how is the meshing for the artery problem implemented?
The first part of your question is a very interesting question and very keen observation. If you look at the immersed boundary method, when we impose the velocity boundary condition, and if it is no slip condition, velocity should be 0. And I showed you in the end, we did this error estimation on velocity just to make sure how accurate we had imposed it. And there was up to 3% error in some parts for the imposition of the velocity boundary condition. That means that the energy directly in the wake of the cylinder is slightly higher than it would be if you had imposed this as a strongly imposed boundary condition with 0 velocity on this boundary. So when you look at the velocity fluctuations and look at the spectra, that gets reflected in slightly higher value. And this is what I think is the reason that we see a slight higher value compared to the case where it was computed with respect to applying it strongly. So that is the part one of your question. Second part is, how do we make the geometry for the artery? We have used Abacus to generate it. And if you have developed geometries, complicated geometries, you realize that it takes a tremendous amount of effort. And if you have to make nodally matched meshes for the solid and fluid, it can be a very big restriction on model development. So we developed it using Abacus features, and we have coarse mesh for the artery. And after that, we simply couple it with the method that I presented.
Thank you very much. So just to clarify, the extra energy was not from the VMS closure, but it was from the slight inaccuracy of the Dirichlet condition of velocity on the surface.
This is what I believe, because we have done the looked at the closure model in a couple of different papers. One appeared in IJNMF last year, where we looked at the case that if the boundary conditions are imposed strongly, then VMS-based closure models that we derive are able to capture the DNS results very accurately. So this energy in the wake flow is due to slight inaccuracy because we are applying the essential boundary conditions.
Thank you very much. Great talk. Thank you.
Okay, great. Thank you. Our next question is from Zhe Zhao. Zhe Zhao, could you unmute yourself and ask your question?
Okay.
Thanks.
Okay. Hi, Professor Mas. Very impressive presentation. And I have two questions about the fluid structure interaction part. I see when you talk about interface coupling part, you consider both fine scale and coarse scale quantity continuities. So I wonder, actually, this is a I have never seen a model with so much details before. So my question is, for this part, which has larger contribution, which is dominant, fine scale or coarse scale?
Yeah.
And by what portion?
Yeah. So when we assume that the velocity field has a coarse scale and fine scale part, then by default, the continuity equation will inherit that split. Now, that split actually helps, and since we are not using a split of the Lagrange multiplier, so the continuity equation will only stay in the coarse scales, right? So coarse scale equation will have fine scales and coarse scales, but since we have not done a fine scale split of the Lagrange multiplier, so fine scale model will not have it. But that is not any disadvantage, because we use rather the coarse scale continuity equation, and it's having the fine scale velocity embedded in it as another equation, a second equation, to extract an expression for Lagrange multiplier. So you're right that these ideas are relatively new in the context of FSI, I would say, and in domain coupling methods for multiple PDEs. If it is the same PDE on both sides, one can use Nietzsche type methods. If it is the same equation on both sides, same order polynomial, and element sizes are same, you can use Nietzsche methods. But if the polynomial order is different, if the element size is different, or if you are undergoing large deformations that will bring in geometric nonlinearity into the system, then you're better off going through an analytically derived Lagrange multiplier that accounts for all of these features.
Oh, okay. Yeah. Okay. Thank you. And my second question is, currently we have some topics where the velocity is no longer continuous across the interface. For example, we have some chemical reaction or evaporation on the interface. So can you give me some suggestion on this kind of problems?
Yeah, a good question. And what you are facing is exactly what you will face if you are coupling Darcy and Stokes at the interface. For example, in Darcy equation, you can only impose the normal, you have to keep the tangential component of velocity as unknown. So you can impose the continuity in the normal direction. Whereas Stokes requires conditions both in normal and tangential direction. So when you couple Darcy and Stokes equations, so I'm giving you as a model problem. So when you couple them together at the interface, while you can prescribe both velocities, both components of velocity for Stokes, you cannot do it for Darcy. So for that, people have developed some interface coupling equations, or called transmission equations or slip equations. Within this framework, you can absolutely account for that. And that was one of the reasons when I was explaining on slide number 3 or 4 about the structure of VMDG method. I said that Lagrange multiplier alone cannot account for interfacial physics if there is some interfacial physics taking place. It becomes very, very clear if you are doing crystalline materials or solid surfaces slipping past each other. In the case of fluid mechanics, you see that right away when you're trying to couple Darcy and Stokes equations. And in your case, if you have situations in which you have discontinuous tangential velocities, you can apply this method. If you send me an email, I'll send you a couple of papers. They'll give you some ideas how to do that. We have done it both for case of solids, where we have looked at slip between solid surfaces. We have also done it for Darcy Stokes. And you can take those ideas and implement them, and they should work.
Oh, okay. Learned a lot. Thank you so much, Professor.
Okay, thanks, Zhe. Any other questions? Okay, Arif, I have a question. I'm really impressed by the results from your method for the flow past the sphere at Reynolds number at 10,000, especially I mean the accuracy, right, from immersed boundary method agreeing with DNS result from mean fluctuation until the second order statistics like dissipation production.
Right.
I have also computed this problem a long time ago. I realized that for the when the Reynolds number is very high for VMS, actually you can capture the pressure very well, but for friction stress coefficient, it seems even you use boundary fitted mesh, and your resolution, if your mesh resolution is not very high, it seems we still have a very significant discrepancy for that prediction. I wonder whether you have any thoughts on improve the accuracy to predict this type of quantity. I know for other quantities, all the results, are already excellent.
Right.
Yeah.
So you're talking about the viscous stress effects, right?
Yeah, that's right.
So
That's right.
Viscous stress effects are going to get dominantly affected by the velocity components, the rotational part of the component there. So if you look at the velocity fluctuations in here, and if so, I've not calculated that specifically. But if you look at the fluctuations, what we showed in our calculations, when we look at the kinetic energy is primarily looking at the velocity fluctuations. So if the kinetic energy is reasonably accurately represented, then those components of velocity, when plugged it into your constitutive model, should give you the required stress, viscous stress components. But we can look into it. But my feeling would be that if your velocity, your velocity fluctuations are right, then viscous effects are dominated by velocity.
Okay. I see. Yes, thanks. Thank you, Arif. Any other questions? Okay. If we don't have any questions, let's thank Professor Arif Masud again for this wonderful presentation. And
thank you very much.